Let's talk about using discrete dynamical systems to analyze predator-prey population growth. In the redwood forest of California, dusky-footed wood rats provide up to 80% of the diet for the spotted owl, the main predator of the wood rat. Here's what a dusky-footed wood rat looks like, and there's a spotted owl. Denote the owl and wood rat populations in month t by the vector O of t, R of t, where R of t, the rat population, is measured in thousands. Suppose O of t plus 1 equals 0.5 O of t plus 0.4 R of t, and R of t plus 1 equals negative p times O of t plus 1.1 R of t. Let me show you what these numbers mean and why they seem reasonable. What does the 0.5 mean? If R of t is 0, in other words, if there are no rats whatsoever, then the owl population next month will be only half of what it is this month. If you kill off all the rats, that owl population decreases by half each month until they're all gone. How about the 0.4? What does the 0.4 mean? The bigger R of t is, the greater the owl population is at time t plus 1. So notice, if R of t is big, that's going to make O of t plus 1 bigger. If the rat population is bigger, that's going to help the owl population to grow. All of this stuff's the same. Here, p is a constant greater than 0. What does negative p mean? The bigger O of t is, the smaller the rat population is at time t plus 1. So again, because this is a negative number in front of the O of t, that means if O of t is big, this factor will be a negative factor, sizable negative factor, and that's going to decrease the rat population. That's because if you have a big owl population, that causes a decrease in the rat population because owls eat rats. Actually, 1,000 p is the number of rats eaten by one owl in a month, because remember this R of t, that's the rat population in thousands. And lastly, what does the 1.1 mean? If O of t is 0, in other words, if there are no owls whatsoever, then the rat population next month will be 1.1 times what it is this month. So in the absence of predators, the rat population grows 10% a month. Not a pleasant consideration. So again, we've got these factors. Express the above equations in terms of matrices and find the eigenvalues and eigenvectors of the matrix using software. Let p equals 0.104. So when we plug in 0.104 for p, we can rewrite these equations as a matrix equation. Because, for example, when you multiply this matrix by this vector, the first row is going to be 0.5 O of t plus 0.4 R of t. It's exactly what we have here. And then this bottom row here would be the second row. We have x of t plus 1. So we're going to write this as x of t plus 1 equals a times x of t. Matrix A is what we call the stage matrix. The eigenvalues of A equals 0.5, 0.4, negative 0.104, 1.1 are lambda equals 1.02, 0.58. The corresponding eigenvectors are 10, 13, and 5, 1. What are we going to do with those? Why did we calculate those? You'll see in a moment. Determine how the owl and rat populations change over time. This matrix has two linearly independent eigenvectors. We just saw that, 10, 13, and 5, 1. We found those using software that's freely available online. So they form a basis for R2, because R2 is two-dimensional. You have two linearly independent vectors. Any two-dimensional vector x can be expressed as x equals c1, 10, 13, plus c2, 5, 1, because again, those can form a basis for R2. Suppose x of 0 is c1 times 10, 13 plus c2 times 5, 1. X of 1 is a times x of 0. Remember we saw a moment ago that x of t plus 1 is a times x of t? We're going to apply that here. So x of 1 is a times x of 0. In other words, it's going to be c1a times 10, 13 plus c2a times 5, 1. Because a is just a constant. So even though the a started out over here, you can just move it on the inside like that. But that's going to be equal to C1 times 1.2, 1013, plus C2 times 0.58, 51, because they are eigenvectors. And remember that A times 1013 is going to be the same thing as 1.02 times 1013. And A times 51 is the same thing as 0.58 times 51, because those are eigenvectors for A. Similarly, x of 2 is A times x of 1. That's going to be A squared times x of 0. So it's going to turn out to look like this. C1 A squared 1013 plus C2 A squared times 51. In other words, it's going to be C1 times 1.02 squared times 1013 plus C2 times 0.58 squared times 51. In general, x of n is going to be C1 times 1.02 to the n times 1013 plus C2 0.58 to the n times 51. As n approaches infinity, the second term approaches 0 because of the 0.58 to the n. As n goes to infinity, this term gets smaller and smaller and smaller. It's going to 0. And so x of n is more or less equal to, it's not exactly equal to, but it's more or less equal to, it approaches C1 times 1.02 to the n times 1013. This implies that both populations grow about 2% per month. That's because, notice, you've got the 1.02 to the n. So the populations are growing 2% a month, and they maintain a ratio of 10 spotted owls per 13,000 dusky-footed wood rats. Again, it's not 10 owls and 13 rats, because the rats are measured in thousands. Thus, only the larger eigenvalue is significant long run, and we can ignore all of this stuff. So that's why eigenvectors and eigenvalues are useful in the analysis of the growth of populations when we use discrete dynamical systems.